Okay, let's go to our next set of notes for Unit 3, Sensation and Perception. This is the video on hearing or audition. Okay, so audition is the technical term for our sense of hearing. Let's start by doing a little bit of review of frequency and amplitude. So frequency in terms of hearing is our pitch, okay? So the high or low sounds that we hear. The frequency is determined by wavelength. Again, remember that wavelength is the length of, or the distance from the peak of one wave to the peak of another. How long it takes for one wave to get to you, right? So here are long wavelengths, here are high wavelengths. We can hear sounds from about 20 hertz to about 20,000 hertz. However, the best hearing is around 30,000 to 40,000 hertz. And then a higher frequency, so these waves here, means a higher pitch of sound. Okay, so those really, really high, like flute sounds or like someone screaming, and then these low or these long wavelengths means that, or lower frequency means a low sound, like a tuba or a low voice or Ryan Mataska's voice. The intensity of the sound is the loudness, okay? So intensity is measured by our amplitude. So the height of the wave. Remember how we talked about the waves in a wave pool? If there's more water, it's more intense, right? So it's louder. So the louder the sound, the higher the wave, the taller the wave. Loudness is measured in decibels, and we hear a range of different decibels. So 0 decibels would be our threshold of hearing, the amount of sound that we need in order to be able to hear something. 10 is just audible, okay? And 20 is about leaves rustling outside when the wind is blowing. 30 is about a library or in your bedroom at night, okay? 50 is going to be like your background noise in the middle of your neighborhood. 70 is like kind of just normal noise, sidewalk, passing of a car, passing of a bus, okay? 80 is going to be a little bit louder. A typical airline or airplane taking off 3 miles away is about at 90, okay? If you're on the platform and a train passes, that's going to be at 100. Rock concerts are going to be at 110. An air raid siren is going to be at 120, and up from there, okay? Okay, next, we're going to go over the parts of the ear. You do need to know all of these different parts of the ear, just like you need to know the different parts of the eye, as well as how sound waves travel from the outside world to our brain, okay? So we're going to start with the pinna. The pinna is the funnel shape, the outside part of your ear right here. That is, it looks like a funnel, right? It funnels in the sound waves. The sound waves come in from over here, and they travel through this auditory canal. This is the part that you can stick your finger in, stick a Q-tip in, okay? At the very back is the eardrum. It's also called the tympanic membrane. Tympanic is spelled right here for you. But the eardrum is also called the tympanic membrane. The eardrum is a soft tissue that is at the back of your auditory canal, and it vibrates with the sound waves. Okay, so think of it as like the outer layer of a drum. That's what the eardrum is. So all of those things right there make up our outer ear. Okay, so those make up our outer ear. Our middle ear are going to be the bones of our ear. There's 3 of them. There's the hammer, which is here, the anvil, and then the stirrup. The stirrup is over here, and the stirrup is what bangs on top of this semicircular canal here. There is fluid inside of this semicircular canal. The semicircular canal, that fluid in there is actually what keeps our balance. It's our vestibular sense. So that's what allows you to balance. But that fluid, when that stirrup bangs on that semicircular canal, the fluid moves. It actually has waves, right? Like waves in water. And that fluid then moving goes into the cochlea. The cochlea is this snail-shaped structure right here, okay? And inside the cochlea is the basilar membrane. And the basilar membrane contains a bunch of different hair cells called cilia, okay? And those hair cells are the actual point at which transduction happens. Remember, transduction is the point where waves are transformed into neural impulses. So these hair cells that wave in the water or the fluid that's inside of the basilar membrane, that movement is going to change the sound waves into neural impulses, okay? So think of those cilia, those hair cells, as like seaweed at the bottom of a lake, right? They flow with the waves, and that's exactly what is happening. The auditory nerve comes off the back of the cochlea, and then those neural impulses that were transduced inside the basilar membrane get sent from the auditory nerve to the thalamus, and then eventually to our auditory cortex. So let's talk about the cochlea. The cochlea is a fluid-filled tube in the inner ear. And like I said, inside of the cochlea is the basilar membrane, and inside of the basilar membrane are those hair cells. That is where the transduction happens. Okay, so let's watch a short video of the journey of the sound going through the ear.
Take a trumpet, for instance. When it's playing, it makes sound waves. The outer ear catches the waves, which then travel through a narrow passageway called the ear canal. The sound waves reach the eardrum, which is a membrane roughly half the size of a dime. They make the eardrum vibrate, which in turn vibrates three tiny bones called the malleus, incus, and stapes.
You need to know the hammer, the anvil, and the stirrup.
Increase the sound vibrations and send them to the cochlea. The cochlea is shaped like a snail and is the size of a garden. It is filled with fluid, and the sound vibrations make this fluid ripple, which creates waves. Hair-like structures called stereocilia sit on top of hair cells and are grouped together as hair cell bundles inside the cochlea. The hair cells inside the cochlea ride these waves, and the hair bundles are moved. The hair bundle on top of the hair cell turns these movements into electrical signals. As the hair bundles are moved, ions rush into the top of the hair cells, causing the release of chemicals at the bottom of the hair cells. The chemicals bind to the auditory nerve cells and create an electrical signal, which travels along the auditory nerve to the brain. Different hair cells respond to different frequencies of sound. The hair cells at the base of the cochlea detect higher pitched sounds, such as a piccolo or flute. The hair cells toward the top of the spiral detect progressively lower pitched sounds, such as a trumpet or trombone. At the very top or apex of the spiral, the hair cells detect the lowest pitched sounds, such as a tuba. The auditory nerve carries the electrical signal to the brain, which interprets the messages as sounds that we recognize and understand.
So let's talk about the different theories of hearing or audition. So the first is frequency theory. And frequency theory states that the rate or the amount of waves traveling up the auditory nerve matches the frequency of a tone. So the idea is that if you have a lot of waves, right, a very frequent amount of waves, the hair cells are going to move at that same space or same speed then, and that determines the pitch. The other theory is place theory, which is what we just saw in the video. Place theory suggests that the hair cells at different parts of the basilar membrane perceive different pitches. So Frequency theory, it's the idea that the amount of waves determines the pitch, and then those hair cells, how fast or how slow they're moving, is the pitch that we hear. Place theory is certain hair cells perceive certain pitches. Okay, these are both theories. So right now they are both accepted in the psychological community. Some scientists believe in one, some believe in the other. So there's a lot of research that still needs to be done. Okay, localization of sound. So because we have two ears, they're on either side of our head, the ear that the sound reaches first is how we determine where that sound is coming from. So sometimes you'll see a dog who hears something weird and they like cock their head, right? They're trying to like open up one ear to determine where is that sound coming from. Okay, and so when we hear something, usually we can turn our head to determine which way it is coming from. That's because wherever the sound reaches first, that's where we can localize the sound from. Let's talk about hearing loss. So just like when you drive your car off of a lot, it depreciates immediately, right? Same thing with your hearing. As you use it, you lose it. This is called noise-induced hearing loss, and this is over time. Because you are using those hair cells, they get tired and they get damaged. And over time, you then lose some of the ability to hear certain pitches. My hearing is worse than yours because I am older and my hair cells have been used longer, okay? Generally, any sound that produces tinnitus, which is the ringing of the ears, causes damages. So anything over that 85 decibels range causes damage to those hair cells, but it just happens over time. So we all have this noise-induced hearing loss. That's why older people sometimes can't hear as well. High-intensity sounds can actually tear off the hair cells of the inner ear. So that is something to make sure that you're not putting really, really, really loud music in your ears because you can damage some of those hair cells, which are irreplaceable. So there's also two different types of actual hearing loss. So conduction deafness is hearing loss that is caused by damage to the mechanical systems that conduct waves to the cochlea. So anything in front of the cochlea, okay? So that would be the bones in the ears, the eardrum, the auditory canal. Anything that is damaged there, that would be conduction deafness, meaning that those pieces are not able to transfer the sound waves, okay? This may be corrected, okay, corrected in quotation marks, helped with surgery or hearing aids. The other type of hearing loss is sensory neural deafness. Sensory neural, sensory being sensations, neural being like nerves, right? So this is hearing loss caused by damage to either the receptor cells, so the hair cells in the cochlea, or to the auditory nerve themselves. Okay, so this is sometimes called nerve deafness. So this is actual damage to the receptor cells that transduce the sound waves to neural impulses, or to the auditory nerve, which transmits the neural impulses to the brain. This is permanent. This really can't be corrected. However, the cochlear implant is an electronic device that can provide a sense of sound to someone who has nerve deafness. An implant, the cochlear implant, which you can see here, does not restore normal hearing, okay? What the cochlear implant does is it gives a deaf person a useful representation of sounds in the environment. So basically the cochlear implant is acting as those receptor cells or the auditory nerve. So it's taking the place of it. And then, so we're not repairing that nerve or those receptor cells. We are truly just kind of like replacing it with another device.